Last time we derived this equation here from the radial Schrodinger equation. The radial Schrodinger equation contained the function phi of r. And in order to rewrite it like this, we defined the function chi of r. And chi of r divided by r gave us the function phi of r, according to this expression here. Therefore, if we manage to find a solution for chi of r, we can write down a solution for phi of r. And from phi of r, we can construct the solution to the stationary Schrodinger equation. If you recall, the stationary Schrodinger equation, or the time-independent Schrodinger equation, could be split into two equations by using the method of separation of variables. One equation, which was the radial Schrodinger equation, and the other one was the equation for the second, so it was the eigenvalue equation for the square of angular momentum, L squared, if you recall. But we didn't care about that, because we don't really want to construct the solution in this case. The objective of this course is to find the discrete spectrum of the energy, how to derive the discrete spectrum of the energy. And we will see that the discrete spectrum of the energy will be derived from here, from this equation here. So we are now interested in analyzing this differential equation. And it is not very trivial, because this is a second order differential equation, but the coefficients of the equation, as you can see here, contain powers of 1 over eta or 1 over eta squared. Okay, so the coefficients are not constant. Otherwise, it would have been very trivial to solve it by using the standard approach for ordinary differential equations with constant coefficients. And plus, it is linear. It is still a linear differential equation, a linear ordinary differential equation, but the coefficients here are not constants. So what we want to do now is we want to analyze the behavior of this equation here. So let me put it here. Behavior of the ordinary differential equation when eta is large. Why do I want to do this? Well, I want to show you why, because in this case, if we now try to analyze the behavior when eta is very large, the second derivative of chi with respect to eta will be of the order of 1 over 4 times chi, because these terms here will be negligible with respect to 1 over 4 when eta is very large. Therefore, we can try to find a solution for this, let's call it equation. So this is an approximate equation as eta goes to infinity, and we can try to find a solution, and that will guide us to find the solution to the more general equation. Now, this one is easy to calculate, and it can be calculated by associating an algebraic equation with the differential equation. In particular, instead of writing the second derivative, I will replace it by s squared, and in place of the zero order derivative, which is the function itself, I will just replace 1. So s squared will be approximately equal to 1 over 4. And this will give you s approximately equal to plus or minus 1 over 2. And the solution, chi of eta, will be of this kind. It will be either e to the minus or e to the plus 1 over 2 times eta. Okay, and it's easy to check this solution satisfies that equation there. Okay, or maybe you could have searched for a solution like this: to some power e to the beta times eta, and then if you substitute it in the ordinary differential equation, you can find that beta squared times e to the beta times eta should be approximately equal to 1 over 4 times e to the beta times eta. And from here you get that beta squared should be approximately equal to 1 over 4. Okay, so it is exactly coincident with the equation that we have there, where instead of beta we have s. So I could have called it s as well instead of beta. Okay, so this is what I could have done. And so we have this solution, but only one of them is acceptable. Okay, because we have to choose the one with a negative sign. Why do we have to do that? Well, because if eta goes to infinity, the solution with the plus sign is not acceptable because it explodes. Okay, we have to find physical solutions. Therefore, we have to choose the minus sign there. Okay, so when eta goes to infinity, the behavior of the function is very close to this one, e to the minus 1 half times eta. Okay, but now let's assume that the function eta, the function chi of eta can be written as e to the minus 1 half times eta. That's still the same. And then here I will put some function q of eta, like this, where this function q of eta here should not grow too fast or faster than this exponential. So we have an exponential here which decreases very rapidly. So this function cannot grow very fast, because at infinity the behavior of the function chi should be dominated by this term here. So this function should not be dominating this expression here. And now we will try to find an expression for q of eta, and I will write it. I will write it probably in the next video. But now let me tell you that q of 0 is equal to chi of 0 from there, right? Because the exponential is equal to 1 when you set eta equal to 0. But chi of 0 was equal to 0. So also remember this, that q of 0 should be equal to 0. And we can substitute this expression for chi in the differential equation above. So this differential equation here. And in order to do that, we have to calculate the second derivative of chi. So first I have to calculate the first derivative of chi with respect to eta, and this is equal to the derivative of that. Okay, so it is minus 1 half e to the minus 1 half eta times q of eta plus e to the minus 1 half eta times dq over the eta, and then the second derivative of chi with respect to eta is equal to the derivative of that. So I have 1 over 4 e to the minus 1 half eta times q of eta plus we have e to the minus 1 half eta d squared q over d eta squared. But we also have another term like this. It is minus e to the minus 1 half eta dq over the eta. So here I have simply done some algebra. In order to obtain this term, you have to take the derivative of this and the derivative of this, and then you add them, and you will find this term here. Okay, and now what I need to do is I have to substitute this expression in the ordinary differential equation. So that's just some algebra, and I will not do it here. It's straightforward, so I will not do it here. You can manipulate the ordinary differential equation with just a few steps, and you can find that you get d squared q over d eta squared minus dq over d eta minus lambda over eta plus L times L plus 1 divided by eta squared times Q equal to 0. So this is another differential equation for Q. And if we find Q, we find chi, okay, because chi is written like this. So we are searching for a solution in this form. Okay, and we will see that this will give us the discrete values of the energy. But I will address this ordinary differential equation in the next video.